Okay, we're looking at a problem here that will give you complete idea of how to do the problem that we did before this, which was number 19. No, number 19. Okay, in number 19, what we did is first of all learn a new way to balance an equation where you have an odd-even problem. The odd-even problem, or thing that was giving us fits with this guy, was getting this guy balanced. Okay, because oxygen has a subscript of 2 in O2, and over on the right side, you'll see water both with carbon dioxide here and also oxygen with carbon dioxide or oxygen with water. And because it's in two places, that creates some real challenges for us. So we balanced, first of all, the carbon on the left with the carbon on the right. And since there were 4 on the left, that's why we started out with a coefficient of 4. Then we balanced the hydrogens on the left, which were 10, with the hydrogens that were in water, okay? And how did we get an 8 here? Yeah, this guy is not an 8, it's a 5 that's crossed out, okay? It's a good thing we recorded this because you would see it that way. Yeah. Okay, so let's make this little line a little bit longer so it looks more like a cross out. And now you can see the 5 more accurately. And so that balanced the hydrogens. And then what we did, instead of trying to get the right numbers on both sides in even multiples, okay, I just told Faith to go ahead and use 1/2 of the total number on the right. Okay, so the total number on the right was 5 oxygens and 8, 13. Okay, that's 5 and 4. Okay, 8 plus 5, 13. Okay. What? Yeah, it was 13. To get the 13 oxygens, you had to have 6.5 as the coefficient. Okay. Then what we did is we went back and we multiplied everything by 2. So that's why we have a coefficient of 2 here and a coefficient of 13 here, because that's 2 times the 6.5. We have the coefficient of 8 here and a coefficient of 10 here. So that was the balancing thing that we did there. And the reason that you see this guy in here is to tell you that no matter what the gas is, for gases, 1 mole of any gas at the same temperature and pressure is equal to a mole of any other gas. And so for gases only, which is what I was trying to indicate here, only for gases, you can use the coefficients, and let's circle the correct coefficients, and then we can talk about those here and here. The final balancing gave us those as coefficients. We not only have a mole ratio and a molecule ratio, but we also have a volume ratio. Because this reaction is going to happen in a vessel, and everybody's going to be under the same conditions of temperature and pressure. And so the volumes will be that ratio within that particular set of conditions. So back on this problem, we're going to use the same little trick that we just found out about. We have the balanced equation. We have the given and find. Okay, here's our balanced equation. And now all we have to do is start out with our number of liters, which was 0.660 liters of O2 over 1, given over 1, just like always. And now we use the mole ratio after we figure out what's on the bottom, which is liters of oxygen. So we got liters of oxygen down here, just like we do in all stoichiometric problems. And now we have to get the ratio. What's the number that goes with liters of oxygen? 1. Okay, the coefficient for this guy right here is a 1, and so that goes here. What are we trying to change to? What two? Liters of CH4. Okay, and the number in front of CH4 or methane is a 2, and it's a simple problem to solve. Okay, 2 times 0.660, so it's 0, 1, 2, carry the 1, 1, 3, 1.320, and we get rid of this because we actually only have 3 sig figs, and this is liters of methane. And that's how we solve that little dude.